Hello, and welcome to Fueling the Transition, a series of podcasts from AFRY Management Consulting. My name is Matt Brown. I'm Vice President in the Management Consulting Division at AFRY, and this series of podcasts will be exploring the energy transition and the key themes and trends we see, driven by decarbonisation, digitalisation, and decentralisation. I'm really pleased today to say we have Graham Cooley with us from ITM Power. Hi, Graham.
Hello, Matt. Delighted to be here.
Delighted that you are here. And with me also I've got a colleague, John Williams, who looks after our hydrogen expertise cluster. Hi, John.
Hi, Matt. Nice to be joining you again.
Very good. And I think we'd kick right off, Graham. Could you explain a little bit about ITM and your role there, please?
So I'm Graham Cooley, the CEO of ITM Power. I've been the CEO now for 12 years. ITM Power is an electrolyser manufacturer. Actually, ITM moved in this year to the world's largest electrolyser factory, which has a capacity of 1 gigawatt per annum. That's 1,000 megawatts per annum of electrolyser production, and we're in Sheffield. And my background's the power industry. I was business development manager at National Power and then International Power, with a particular interest in energy storage.
Just a bit of background about you, Graham. What's your main motivator? I know you've been in the energy industry for many years, a lot of experience. What is your motivation, your purpose in your work or in your life in general?
Yeah, interesting question. So I started in the power industry and was very interested in renewable power. I guess back in the day when companies like National Power and most power companies didn't believe in renewable power, I then concentrated on energy storage, particularly storing renewable power. So we built Regenesis, which was the world's largest electrochemical energy store, 100 megawatt hours at Little Barford. And then I moved into other renewable technologies. And Metalysis was set up to extract tantalum to make supercapacitors, and now green hydrogen with ITM Power. So my motivation has always been introducing new technology, scaling that new technology so it can have an effect on the energy industry and the energy transition in general. So what motivates me really has always been environmental issues. In fact, my parents were environmental campaigners.
What sort of thing were they? There must have been some time ago before sustainability and issues around sustainability were so mainstream, quite ahead of their time, I would guess.
Yeah, I think so. I mean, my father was a trade union leader. He was actually one of the people responsible for the Lucas Workers Plan for converting armaments production into socially useful production, including a technology for the energy transition and environmental issues. He won the Right Livelihood Award in 1981 for his work. So, and my mother was an environmental campaigner as well. So, a background throughout the whole of my life looking at environmental issues.
And sounds like you're quite rightly proud of what your mum and dad achieved.
The pride's not a word I'm particularly interested in, really. I think, there's a lot of work to do. And I'm not particularly proud of where the world is right now. And I think we all need to put our backs into the energy transition or we've got a serious problem.
Yeah, that is without question. I think I'd agree. Risk of catastrophic climate change is ever present and growing, and there's a huge amount to do still. I know sometimes people feel like with all of the news about renewables and hydrogen and so on that the battle's already won, but of course we're really still right at the beginning of the battle as well on that one. I think even before we start thinking about the other transitions we've got to make across, say, food and agriculture, for instance, if we're going to be able to move to a much more sustainable footing.
Yeah, absolutely. I mean, people for years have talked about we will see the effect of climate change soon, And we are now seeing it. We're living through it right now. And it is absolutely fundamental that COP26 produces some very significant results, because humanity is in a very serious position right now.
Yeah, and I think we all have hopes for COP26. Let's hope we can see some progress there. So I suppose moving on then a little bit to ITM and recent developments. I understand there were some announcements made recently by ITM. I wonder if you wanted to just fill us in on those, Graham.
Sure. So we announced last week a funding round. Actually, we raised $250 million to expand our capacity. So expand our capacity from 1 gigawatt per annum to 5 gigawatts per annum by 2024. First thing to say is that in the UK, we're in the world's largest electrolyser factory with a capacity of 1 gigawatt per annum. That's 1,000 megawatts per annum of electrolyser manufacturing capacity. We're going to be building a second gigafactory in the UK, 1.5 gigawatts per annum. And that factory will be built in parallel with sweating the asset that we already have. And the second gigafactory will be more highly automated. And we're implementing automations so that we can drive down costs. We will then, by the end of 23, have 2.5 gigawatts of manufacturing capacity in the UK. And we have further resources to get to 5 gigawatts internationally. So that's the plan. Our backlog today is 310 megawatts, and we have a tender pipeline. That's the number of quotations we've made against international tenders of 1,011 megawatts. So that's just over a gigawatt for the first time. And I can tell you that the industry is moving incredibly quickly.
In terms of the overall scale, I mean, John, I don't know if I can bring you in here. The numbers that people talk about when we look at various plans, either European or UK or global, in terms of electrolyser capacity, what sort of numbers are people talking about?
Yeah, it's a good question. So in Europe, the EU hydrogen strategy was published last year. That has a target of 40 gigawatt of electrolyser capacity by 2030. A number of countries have published national strategies. So countries like the Netherlands, Spain, Germany, Portugal, and they have varying targets, but the most common seem to be around 4 to 5 gigawatt by 2030. In the UK, interestingly enough, they've published a target in the hydrogen strategy for 5 gigawatt, but of low carbon hydrogen production capacity, which would be a mixture of both hydrogen from natural gas with CCS and green hydrogen. So, for ITM to have the capacity to produce 5 gigawatts is pretty significant, I think.
And do the pipelines people talk about, when we look at some of the numbers that get bandied about, Graham? Have you seen, I quite often see some big numbers that people talk about in terms of pipelines. Obviously, You're building your capacity out quickly, but how do you feel about some of the numbers we see sometimes?
So perhaps I could just add a couple of things to what John said. So the EU target is 40 gigawatts by 2030, but also includes 40 gigawatts of imported green hydrogen. And that 40 gigawatt target is an electrolyser target. If you add up all of the national schemes around the world, then the target is 150 gigawatts to 2030. A very significant number is the IEA report, which says that the world needs 3,500 gigawatts of electrolysis to get to net zero by 2050. So that's in 29 years. So if you look at that number, 3,500 gigawatts, that's 35 centuries of the production in our factory, which is the world's largest. So there's some scale up to be done. And if you look at the cost of a full system, green hydrogen system, including electrolysis and the balance of plant, that's about £500,000 per megawatt. So 3,500 gigawatts, it is around $2 trillion of market.
There's some big numbers being talked about, but the ability currently of us to meet that seems quite remote. Is that true?
We're expanding to 5 gigawatts per annum of production, and that compared with 3,500 gigawatts in the next 29 years is pretty small. But one of the key things is that when we did our fundraising, we got backing from the capital markets. And actually, the capital markets now are increasingly understanding green hydrogen, the importance of manufacturing electrolysis equipment around the world. And you can't make the energy transition without the backing of the capital markets. So I feel very confident, actually, that as this market develops, and it is developing incredibly rapidly now, we're on the bottom of an S curve, and we're rapidly moving up that S curve. And from what I've seen from the city and the capital markets, I think we'll have their backing going forwards. And I think that's critical.
Yeah, I think that's a really good point. And, from our perspective, we do a lot of work on transactions, and every day we're seeing an increasing interest from our clients wanting to understand more about hydrogen projects, more about hydrogen in general, and about how they can get involved. Where are the good investment opportunities for them in the market at the moment? Sometimes currently, with the still developing regulatory framework and support mechanisms, it's sometimes quite hard to find a really positive business case at the moment, but that is going to improve over time. But certainly, there are lots of opportunities out there for investments in companies like ITM and some of the other electrolyser manufacturers, and indeed all the other companies across the value chain, producers of compressors, transformers, rectifiers. All these are going to really need to be scaled up in the next 5 to 10 years, really significantly.
Playing devil's advocate a little bit, knowing that, say, in the UK, we have some, supply chain issues, and generally around the world, there are issues in many parts of industry and the economy. Are there any concerns in terms of that scale up, would you say, over say the next 5 years that we should be worried about?
So there's an international shortage at the moment of chips and also steel, but I think that's temporary, and I think that will normalise. This is an international market; it's a global market. That the whole of the planet has to decarbonise, and green hydrogen is a very important component in getting to net zero. So it is a global market. Not only are we scaling the manufacturing of electrolysis modules, but we formed a joint venture with Linde. That's Linde Engineering. And Linde are one of the world's largest current suppliers of hydrogen. They're embedded in the oil and gas industry and the petrochemicals industry. And so our plans mean that not only can we scale the manufacturing, but also the deployment. And actually having the right EPC partner, that's engineering, procurement and construction partner, means that we can scale not only manufacturing, but also the deployment. And Linde have very strong purchasing power. And I think that being a medium-sized company in Sheffield is one thing, but having the firepower of the likes of Linde and also our partner Shell, a very important partner for us. We're building the world's largest electrolyser at the Rhineland refinery to make sustainable aviation fuel. We also work with Ørsted and Phillips 66, and large international companies are very important for ITM Power when it comes to the global supply chain. So I think we feel very confident about being able to scale up, not only from the point of view of the electrolysis, but also of deployment.
Well, what about the renewables though, Graham? Because obviously we can have all the electrolyzer capacity in the world, but if we haven't got enough renewables with good load factors, it's really going to affect the scale at which we can produce hydrogen. So just wondering what your view is on that.
No, you're absolutely right, John. I mean, to make low cost and large amounts of green hydrogen, you need high load factor, low cost renewable power. It's absolutely dominant in the cost structure of the green hydrogen. If you take the UK, for instance, we have a target to 2030, so in the next decade, of deploying an additional 40 gigawatts of offshore wind. You're going to need a lot of energy storage. And the best way of storing electrons is to turn them into storable molecules. So, you might look at it the other way around. You might say, with all the renewables that we're going to be deploying, how are we going to implement all of that energy storage? And the way you do that is with green hydrogen. So to me, the two industries grow in harmony together. As you increase renewable power, you need more and more energy storage. You need more and more rapid response demand side loads to balance the network. And that is electrolysis and green hydrogen. So the more that you deploy together, the more you'll be able to deploy going forwards. So, green hydrogen actually allows you to have more and more renewable power on the network. So I think it's growing the two industries together that's the important thing.
And is there, Graham, in terms of ITM's role, knowing that we have probably a massive opportunity space for electrolysers, are there other competitors of yours? Is this an area which is in some ways quite difficult to enter? The competitive barriers are quite high, or is it something that would be possible for more and more firms to be able to help to build up that supply? I suppose that is the future ITM becoming, with fundraising and support, becoming bigger and bigger and bigger. Obviously, that's what you would you'd expect. But will there be other competitors as well also filling that market? Because it seems the space is so huge that we need lots of ITMs.
Yeah, so I think the barriers to entry are pretty high. Let me explain what I think they are, first of all. So at ITM Power, we've been developing PEM electrolysis for the last 20 years. We've been deploying larger and larger electrolysers over that period of time. We've spent over half a decade working with Linde and with Shell on deploying electrolysis, particularly on Shell forecourts or refueling stations. We built most of the refueling stations in the UK. Every 2 years, the largest electrolyser that we have deployed has been an order of magnitude larger. So we started with 100 kilowatt units, then 1 megawatt units, then 10 megawatt units. We're now building 100 megawatt units, and we're now bidding hundreds of megawatts, and the national schemes are at 1 gigawatt. So every 2 years, a scale up of an order of magnitude. That's a logarithmic growth. And we've followed that with reference plant, where we've gathered data. So what would you need if you wanted to follow what we're doing and become a new entrant? Well, we've 20 years of development, reference plant in the field, data, partnerships, manufacturing capacity. We have the world's largest manufacturing capacity, and backing from the City of London. Okay, that's 5 important things. So if you can bring all of those together, then you could probably do it as a new entrant. We do have competitors around the world, and I would say this very simply, that all of those competitors will get projects. I mean, this market is massive and moving incredibly quickly. And I think every electrolyser manufacturer around the world is going to be capacity constrained very rapidly. And that's why we raise money for additional capacity and for working capital. This is, we are a company with the right products in the right place at the right time.
In terms of just for some of the people who are listening, you mentioned PEM electrolyser. Are there other types of electrolyser out there? Is PEM the only one?
PEM electrolysis is they're electrolysers that you can turn on and off very rapidly. So you can couple them to renewable power or use them for balancing the grid. They make high pressure hydrogen. Our two ratings are 20 bar or 30 bar, which you need for most applications. And they make clean hydrogen. In fact, because the hydrogen hasn't seen any carbon molecules, they are actually 5 nines purity when the hydrogen is produced. The only impurity is some moisture, which is very easy to take out. So if you take the older form of electrolyser called alkaline electrolysers, you can't turn them on and off rapidly. You have to clean the hydrogen because it bubbles through an electrolyte called potassium hydroxide, which is a caustic material, and they produce low pressure hydrogen. And the only advantage of alkaline electrolysers in the past was that they were lower cost. And actually now we've scaled PEM electrolysis, and full system costs are comparable. So you have all the advantages of PEM electrolysis at a similar cost, full system price to the customer. So, to me, the future is PEM electrolysis without a doubt.
What does PEM stand for?
Polymer electrolyte membrane. So it's about having a physical barrier between the anode and the cathode. So an electrolyser, it's an electrochemical device, so it has an anode and a cathode, and you split water, water into hydrogen and oxygen. An alkaline electrolyser has a liquid electrolyte, potassium hydroxide, and it transports OH minus ions. A PEM electrolyser has a physical barrier that absorbs the water, and that is a polymer. And that polymer has fixed acid groups, and it transports protons across the electrolyser. Protons are more mobile than OH minus ions, particularly because they are a much smaller molecule and have a smaller hydration sphere. So the consequence of this is that you can have very high efficiency at very high current density, which means that the electrolyser can be compact and efficient, and it means that the production cost of the green hydrogen is lower for that reason.
You said earlier, I think I'm right, you said earlier that storing electrons, the best way to do it is by making hydrogen. I'm guessing some of the battery manufacturers might have a different viewpoint. I just wondering about your perspective on battery technology.
I actually don't think they would have a different perspective, actually. The whole energy storage industry understands how energy storage is segmented. So energy storage is segmented by time. So if you want short duration energy storage, if you want up to an hour of energy storage, you will buy a battery every time. If you want many hours or days or months or even years of energy storage, you make molecules and you store them in the gas grid or you use them for industry. So you have to separate long duration storage from short duration storage. And actually both industries are entirely complementary. And by the way, if you want very, very short-term energy storage, like a split second, you're going to use a flywheel or a supercap. So it's very well segmented market. And perhaps if you want 3 hours of energy storage, you might use a flow cell. So it goes sub a second, you'd use a flywheel. A few seconds, you'd use a supercap. A few minutes to up to around an hour, use a battery. A few hours, you might use a flow cell. But above that, you'll use hydrogen every time.
Well, what about, Graham, using the flexibility of the electrolysers? Because we understand, you've got very, very quick reaction times in electrolysers, so you can switch them on and off or switch them up and down very, very quickly indeed to provide some of that flexibility back to the grid in certain circumstances. If you're running, you can switch down. If you're not running, you have a project, you put a fuel cell in there. Do you see a role for electrolysers to offer that flexibility and grid services?
Very much so, yeah. It's a very good point. So look, you can turn our electrolysers on and off in less than a second. So we did qualify them into enhanced frequency response. There's a new protocol now from National Grid called containment, but which is a half a second protocol, which also works with electrolysis. So grid balancing, then, you can look at grid balancing from the electrolyser point of view in two different ways. First of all is frequency. So the way you balance frequency on the network, by the way, frequency is the obligation of the network operator, and it works at high voltage. So on the high voltage network, you balance frequency with a load, either with a load or a generator. But in the case of an electrolyser, a load. And you can turn the electrolyser on and off in a split second, helping to balance frequency. An electrolyser also works in DC. And at the front end, it has an AC-DC converter. And so it can absorb leading or lagging VAR flow, which means if you're on the plugged into the distribution network, you can stabilize voltage by absorbing either leading or lagging VAR flow. In other words, you can make the electrolyser look like a capacitor or look like an inductor. So you've got two modes which you can operate it in. You can operate it as a flexible load or as a unit that helps you with voltage stabilization. So very much so, grid services are a very important application of electrolysis as a demand side load.
No, I'm sure a lot of the discussions that we have, but internally and also with clients, particularly with the AFRY is a big global engineering with a huge process industries division, and they're talking to clients all the time about decarbonisation and the potential to use hydrogen. Now we've just heard some really good examples of how you can use electrolysers flexibly. What our clients are asking us is, the question is, I've got a very flat hydrogen offtake demand. How can I use an electrolyser which is running variably depending on the renewables it's connected to? How can I use that to meet my flat demand?
So when you look at industry, of course, 70 million tonnes per year of hydrogen is sold into industry. That's grey hydrogen made with natural gas, and that's the entry market, because they are the demand centres. So we're very interested in placing electrolysis equipment at refineries or for methanol, ammonia production, or for the steel and metals fabrication industry. So once you've decided that that's where you're going to put the electrolyser, what can industry do with it? So say you have got a flat demand for hydrogen. How does that help you in terms of grid balancing? So first thing to say is if you have a long-term contract for renewable power and you're making green hydrogen to replace grey hydrogen, you could do that today at a lower cost than grey hydrogen, so long as you have the right electricity price. So everybody used to tell me that required electricity around 2.5 cents per kilowatt hour. Actually, that's not the case anymore, because the cost of natural gas has gone up so significantly. You can make green hydrogen today at a lower cost than industrial hydrogen because of the gas price. So that's the first point to make. A second point to make is that grid services are about grid balancing. You can also use an electrolyser for load balancing. So let me explain load balancing. If you're an industrial user, a very large user of electricity, You buy electricity in a band. So you have an upper limit and a lower limit. So your contract says you'll get electricity at a particular price. So long as you don't go over a particular usage or under a particular usage, you have a lower band and an upper band. And what you can do with the electrolyser is protect yourself from going below the lower band or above the upper band. So as you approach the upper band running an electrolyser, you can turn the electrolyser off, and vice versa if you approach the lower band. And industrial users always know the time of day that they approach the upper band or the lower band. So one of the key applications in industry is to run an electrolyser constantly, and then as you approach the upper band or the lower band, store the hydrogen or use the stored hydrogen. So it is about operating your electrolyser and operating hydrogen storage so that the flexibility of demand is on the electrolyser rather than on the industrial plant.
Absolutely. And we've developed a very neat configuration optimizing tool that can do all that in conjunction with all our power market projections. But the question, I think, coming back to is that's fine if you're connecting an electrolyser to the grid. But if you're connecting an electrolyser to the grid, how do you ensure that your hydrogen is green? You know, we still haven't got a classification system in Europe or in the UK. If the carbon intensity of the grid is more than, just more than zero, so you've got some fossil fuels in the generation mix, surely if you're using that grid power, your hydrogen isn't then green.
Yeah, no, I agree with that. And the purest green hydrogen, and certainly RED 2, Renewable Energy Directive 2, qualified green hydrogen requires you to directly couple to renewable power. And that is the requirement now. But the requirement going forwards will be that you'll be able to connect to the grid and buy a renewable energy contract. And that then means that more renewable energy contracts will be sold, allowing more and more renewable power onto the network. So I think that there's a lot of legislation going through at the moment about being able to make green renewable hydrogen via the PPA route. Couple of things I would add as well. If you look at our project in Humberside, which is connecting 100 megawatts of electrolysis to Hornsea 2, which is a 1.4 gigawatt offshore wind farm. The wind farm has a load factor of 55%. But if you connect 100 megawatts to a 1.4 gigawatt wind farm, you actually get a load factor on the electrolyser of well over 80%. And the reason for that is that when that 55% is an average. And if your first slice of power generation is the electrolyser, then the load factor looks well over 80%. So you can get high load factors by connecting a smaller load to a larger generator. So that's the first point I'd make. Second is sleeving. So you can connect directly to high load factor renewable power and then only have a small percentage being grid connected power, and you can very easily switch between the two. So I think three strategies are direct coupling, PPA route, and sleeving.
Yeah, and I think that's right. And for us, certainly in all the analysis that we've done, looking at hydrogen production cost, the higher the load factor you can get the electrolyser, the much cheaper you can produce the hydrogen and make it much more competitive. So anything that can be done to improve that utilization of the electrolyser, we think is absolutely great. You mentioned RED 2 there. We saw one of the earlier drafts of RED 2 that talked about, having a PPA with renewable power, fine, but then talked about temporal and geographic correlations. So that the electrolyser, even under the PPA, would need to be operating, I think, at that point within a 15-minute window of the power being generated. And that seemed to us, on a first sight, to be quite restrictive. I don't know if you've got any insight into whether that temporal correlation is being relaxed or whether we'll end up with a much wider window.
So I think temporal correlations are all about knowing what type of renewable you're using. Is it solar or is it wind? Is it geothermal? Is it hydro? And actually the correlation is all about, as more and more renewable power comes on the network, turning on more and more loads. So let me tell you what I think the correlation is between more renewables and more load. As renewables come onto the network, the network experiences higher and higher frequency. You get rising frequency, and the way you compensate using a load for rising frequency is turn on the load. Falling frequency, you turn off a load. And so there's a strong correlation between high levels of renewable power on the network and the requirement for demand side management and turning on loads. So I think there is a correlation between the two. I think 15 minutes is quite a wide window, actually. I think if you're doing genuine grid balancing, it's primary grid balancing is 1 second, and secondary grid balancing is going to be anywhere from 4 seconds out to 2 minutes. So that sounds to me like quite a wide window and an acceptable one if you're an electrolyser manufacturer. Very, very easy to turn off in those sort of timescales. But one other point about RED 2, if you don't mind. RED 2 requires all refineries in Europe to make 14% of their product renewably by 2030. And this is why we see such strong traction for electrolysis equipment at refineries. Refineries are one of the largest users of hydrogen worldwide, and RED 2 gives them that obligation. So this is why the Rhineland refinery project with Shell, which is 100 megawatts of electrolysis, is such an important reference plant for us. If you look at the UK and you look at coupling electrolysis to the distribution network, far more of the cost of the electricity going into the electrolyser is distribution charges than it is generation charges. So one of the reasons that direct coupling is incredibly important is you don't pay the distribution charges. And that makes a huge difference to the cost of the green hydrogen.
Sure, and I'm really glad you mentioned the UK, because I wanted to come on to ask you or have some discussion about the UK hydrogen strategy. As I mentioned right at the start, UK has set itself an ambition, not a target, an ambition for 5 gigawatt of hydrogen production capacity by 2030. But the UK is adopting what it calls a twin track approach, where that hydrogen production target will be both blue and green. And looking at some of the industrial clusters and the hydrogen production targets for blue hydrogen in those, does it leave much room for green hydrogen? And then coming on from that, do you think the UK is missing an opportunity to put more emphasis on green hydrogen rather than blue?
Yeah, so a great question. So I've been saying for a decade to the UK government that blue hydrogen is oil and gas business as usual. It uses the existing natural gas infrastructure, which leaks. And if we're going to produce hydrogen from a leaky natural gas infrastructure, then we should be booking the emissions from the infrastructure to the kilograms of hydrogen. You make hydrogen by reforming natural gas and CCS, and the capture isn't complete. You can't get complete CO2 capture, and the technology for CCS hasn't been scaled up and isn't proven. And when you do blue hydrogen, you need a CO2 infrastructure, a separate hydrogen infrastructure, and you need to continue running a natural gas infrastructure. And it's incredibly expensive and you need to do very large schemes. And then my final point would be you're storing CO2 in a depleted oil well, and you're going to be doing that for a very long period of time. And green hydrogen by the mid-2020s will be lower cost than blue hydrogen, regardless of where we are with gas prices. And the point here is that gas prices are going up, not down. And so I think you'll find that any CCS schemes that have been developed will be stranded assets. So I don't know who's going to take the liability on all those CO2 stores, and I don't see why we should be paying for massive CCS schemes that are going to be stranded assets in a very short period of time. Green hydrogen, on the other hand, you can build it in a modular way. You can start the decarbonisation journey immediately, and you don't produce any CO2 in the first place. So there's no need for any storage. Why are the government doing blue hydrogen as well as green hydrogen? Well, I think the oil and gas industry has had an incredibly strong lobby over the years. And I think that the UK government, particularly after the announcement from the EU that they're only doing green hydrogen, and all around the world, every other nation is only doing green hydrogen, I think the penny is dropping in the UK. And I was actually delighted that the hydrogen strategy was announced by Kwasi Kwarteng, the Secretary of State, on the day that he opened ITM Power's Gigafactory in Sheffield. It was a great endorsement of green hydrogen in the UK.
Do you not think, I mean, because we've tended to be colour agnostic when we've talked about hydrogen in a lot of the work that we've done, because we can see the benefits of, the benefits of green obviously are clear. And I think you're absolutely right. There are green hydrogen projects being deployed today, which can make a difference right now. Blue hydrogen is going to take a number of years before it can achieve any kind of scale in production, so mid-2020s at the earliest. But then there's a potential for blue hydrogen to be scaled up quicker, so we can start to replace grey hydrogen. We can then start to use that blue hydrogen in other applications, in transport, for instance. So it can play a role in the scale of production of hydrogen, so we can start to remove the emphasis on grey hydrogen and on diesel or whatever the application is. Do you not see there's a benefit in allowing that earlier production of hydrogen at scale, even if it is from natural gas?
No, John, I don't buy that argument at all. So I used to be in the power industry, and everyone used to tell me you could never scale solar and wind. And that's why those power companies didn't start. And actually, when the industry started and the deployment started, the costs came down as the volumes went up, and it happened very quickly. I suppose the simplest answer to all of this is that green hydrogen will be lower cost than blue hydrogen, and it will simply be market forces that mean that green hydrogen will be dominant. And we'd like to see strategy to kickstart the industry. That's the government's bit. But you will see volumes rapidly increase, prices rapidly come down, and any blue hydrogen schemes, in my view, will be stranded assets. So the scale argument, we're scaling very rapidly. I talked to you about 1 gigawatt per annum of manufacturing capacity, expanding to 5 gigawatts per annum. We're not the only electrolyser manufacturer in the world, and scale up is rapid. The technology is modular. CCS isn't modular. The modules are deployed by an EPC contractor in Linde engineering that deploy crackers of huge volume. So I have no doubt in my mind that electrolysis can scale.
Okay, can I just come back to something you mentioned previously as well about natural gas grids. What do you think the potential is for the conversion of natural gas networks, so onshore transmission and distribution? And then think about that in relation to the discussion that's going on. Again, it's a bit UK centric, but the discussion that's going on about the use of hydrogen in domestic heating. Do you think that is an argument that isn't just going to be won by the hydrogen guys, by the natural gas guys? Do you think the days of gas or hydrogen networks, it's just not going to happen?
So another great question, John. Thank you. So one of our strategic investors is Snam, which is one of the largest gas transmission companies in the world. Second largest, second only to Gazprom. And they're very vocal about green hydrogen and converting the European gas grid to green hydrogen. The EU, of course, has developed the Hydrogen Backbone project, of which National Grid in the UK are a partner. And all over the world now, we see gas transmission and distribution operators looking at converting the natural gas grid to green hydrogen. Why would you want to do that? So first of all, that infrastructure exists. And of course, gas and energy gases are a more efficient way of transmitting energy than copper and electrons. So that's the first point. Second point is, even if you just look at the UK, the gas grid is larger than the electricity grid, actually about, on average, 3 times the size in the UK, and during the winter transmits about 5.5 times the energy that the electricity grid does. We used to have 60% hydrogen in our gas grid in the UK when we ran town gas. So we and gas operators over the years have been very successful about operating gas grids with other energy gases, and particularly across Europe, high gas and low gas. Trials all over the world have shown that you can put 20% hydrogen into the existing gas grid and not change any end user devices. So that's 20%. That is the first threshold. Next threshold for the gas grid itself, the pipes, is going to 60%, which is where we used to be with town gas. In that case, you do need modification of end user devices. And then ultimately, you could go to 100%. Question is, how do you run a gas grid with 100% hydrogen? Well, you need some sleeving. Now, very interestingly, people haven't linked the two arguments, but all over Europe and all over the world, sleeving is essential anyway, because gas grids leak and they need to be sleeved. And so what the gas industry is looking at is sleeving those pipes with hydrogen compliant piping. So the energy transition requires every gas operator, every gas distribution and transmission company to put something that is net zero through their pipes. And frankly, if they don't have a net zero solution, then they won't have a business. So you will have all of those companies, their own gas infrastructure, with a very strong driving force to adopt green hydrogen, because it's the only net zero energy gas.
So in terms of, say, let's look forward, I don't know, 15, 20 years. So we've started to see the take-up of hydrogen at scale in industry. We're starting to develop some uses in transportation, in heavy trucks, maybe in maritime with hydrogen or as ammonia. Let's come back to the question about heat. But from what I understood you were saying earlier on, is that you could connect electrolysers to the grid, which means you could co-locate them near demand. Would you, if you go that route, do you need a gas infrastructure? Can you just produce all the hydrogen near the demand, so you don't need the NTS, you don't need a gas distribution network?
I don't think so. I think for economies of scale, it's better to have very large electrolysis connected to the transmission network, electricity transmission network, or in fact directly coupled to renewable power. You use them then for grid balancing and load balancing, and then you use the gas infrastructure. Small electrolysis connected to the low voltage network doesn't give you the network advantages. You know, the reason that heat pumps are difficult is that you connect them to the low voltage network, which is underground, and you have to dig up the roads, dig up people's gardens to reinforce the low voltage network. You put electrolysis on the high voltage network, you use them as a flexible load for grid balancing, absorbing renewable power. Then you have real joined up thinking between the electricity grid and the gas grid, so-called sector coupling. And I think that's the way of running the network. By the way, if you use the gas grid to transmit green hydrogen, you can also use green hydrogen for power generation, and it gives you a steam cycle. Now, why do you need a steam cycle? This is getting onto a slightly different topic, but I believe that you need some steam cycles, and that would be either gensets working on hydrogen or nuclear. And the reason you need them is that you need grid inertia. The National Grid works in AC, and actually, I don't believe in synthetic inertia. I think you need big rotating machines to give the network inertia. So I would say renewable power, green hydrogen in the gas grid, and using some of it for power generation, as well as most of it for heat.
It sounds like quite a lot of hydrogen, and I don't know whether you've done the numbers from your end, Graham, in terms of how much renewables, how much wind and solar, and is that, or is it that we'll be importing from Saudi Arabia, who obviously have big plans to become a major hydrogen exporter in the future?
Yeah. Okay. So look, I said earlier that that one of the key advantages of renewable hydrogen is that green hydrogen is that when you use electrolysis, you can store electrons as molecules and net zero molecules, and the world only uses energy in two forms. It uses it in the form of electrons or in the form of molecules. And the only way of producing a net zero molecule is to split water with net zero electrons. Now, the consequence of having stored renewable energy in a molecule is then that you can transport it. So what you're able to do then is make a liquid fuel like ammonia or methanol. You can put it in a tank and you can transport it from one side of the world to another. So what you now have is a tradable commodity derived from renewable energy. So if you're in British Columbia and you make hydro, you can export that renewable energy to Japan. And you do that by making a molecule that you either use as liquid hydrogen or you use as ammonia or methanol. And you can put it on a ship and you can transport it around the world in exactly the same way we do with LNG. Right? So not only have you stored renewable power, but you can trade it worldwide. And I think this is a fantastic proposition for the world, because some places in the world have a richness in renewable resources and others don't. And it makes it a renewable energy, a tradable commodity. So I think that is the ultimate proposition for renewable power, is to make it a global thing rather than a localized thing.
But it does have implications, I suppose, in terms of, certainly years ago, renewables were seen as one way of having a form of local security of supply for energy, and it would have implications for those countries which were having to import large amounts of green hydrogen in this scenario, I guess, in terms of but also perhaps in terms of diversity of supply and diversity of in that way. So I mean, obviously there are solutions for that because we face that in different ways already. But I think it's an implication one would take away.
Yeah, I agree with that. If you've got renewable energy resources and you can make your own fuel from those renewable energy resources, then you get fuel security and you also get an improved balance of payments because you're not importing fuel. So it has those two advantages. But then you also have an exportable product as well. So it gives you all three of those things.
Just comment on the argument about the fuel security. I think is a really significant one. If you look at countries like Japan, South Korea are really investing heavily in developing a hydrogen economy. However, they're not necessarily rich in renewable resources, so they will be replacing an oil import and gas import dependency on a hydrogen import dependency. Might change the countries that they're importing from, which they feel more secure about. But it does, in certain countries, it still lead to an import dependency. Also the case in Europe, a country like Germany in their announced targets for hydrogen deployment in industry, etc., are setting themselves up for a pretty significant import dependency. And there are a number of MOUs and LOIs that the German government has now started signing, with Middle East countries, with Chile, with Namibia recently. So the growth and the potential for this global trade in hydrogen and ammonia is really significant and really interesting, I think, going forward.
Yeah, John, I entirely agree with that. And if you look at the UK, we've got one of the world's richest offshore wind resources. We can be a producer of fuel that can be sold internationally. I think it's an incredibly important industrial proposition that the UK government should be much more supportive of.
But how many gigawatts of offshore wind do we need just to replace the heating load in the UK? That's my question. I imagine it's a vast amount compared to what we've invested in today.
So in the UK, there's 300 terawatt hours of energy flowing through the electricity grid and over 800 terawatt hours flowing through the gas grid. And we use about 650 terawatt hours of fuel. So you can use the rule, Matt, 1, 2, 3. So if you take 300 terawatt hours as the electricity grid as 1, then the fuel industry is twice the size, and the gas industry, or heat effectively, is 3 times the size. So you need a lot of renewable power. If you take the target of having 40 gigawatts of offshore wind in the next decade, and you compare that with our electricity peak in the UK. During COVID, actually, our electricity peak in the UK was just under 50 gigawatts. That peak was the lowest it had ever been, 50 gigawatts. When I was at school, it used to be 62 gigawatts. So planting up with 40 gigawatts of offshore wind compared with that instantaneous peak, it's very clear that we're going to need a huge amount of energy storage, and that is green hydrogen.
Just some numbers we ran on the back of the EU hydrogen strategy. So for the million tons of hydrogen, which is around about 40 terawatt hours, I think, we think you'd need probably about 10 to 12 gigawatt of offshore wind to hit the 10 million ton target in 2030. You're probably looking in the region about 100 to 120 gigawatt of offshore wind. Obviously, if that's onshore or solar, then the capacity might be higher. But, it is a significant amount of renewables, which is needed also at the time that you're investing in renewables to decarbonise the power sector as demand stands at the moment. So, coming back to a comment I made earlier, I really don't think we can underestimate the amount of investment that is required in renewables. It really is significant alongside, what is required in electrolyser investments to scale up manufacturing, but also in the rest of the value chain as well, in terms of transportation, whether that's via energy and grids or whether it's via molecules in gas networks. The scale of the challenge, the scale of the investments is quite staggering. But having said that, what we need to think about is the cost of doing nothing. And I think we all agree that we can't do nothing. We've got to face this challenge head on. We've got to make these investments. It seems quite clear that energy prices for end users are going to be more expensive in the future compared to today. But when you look at alternative scenarios for hitting net zero, what we need to do is compare those future scenarios against each other rather than comparing them against today.
I just asked John in terms of energy prices right today, maybe might be a slightly different perspective in terms of where energy prices have gone at the moment.
Could I provide the other side of the equation for John, which I'm sure he knows, which is that today we import half of all of our natural gas. And John's been talking about the large investment required for renewables and electrolysis without mentioning that we import half of all of our natural gas in the UK. So you have to net one off against the other. And that's a huge expenditure every year as well. Now, the next thing you have to consider is what happens when the world eventually values carbon and puts a carbon price. That price of importing half of all of our natural gas is going to go up even more. And so you're netting off even more investment every year into a capital investment in equipment that will last for many years, producing our gas domestically in a renewable way. So many people in the industry love the idea of frightening the general public with the investments that are required without realizing without stating what the savings are. So perhaps I can tell you that the savings are not importing natural gas, which is carbonizing and will be subject to a carbon tax.
And I think that's a very good point. I wasn't arguing it from the point of let's keep a natural gas or let's go a natural gas route only. It's just stating the fact that the investments will be significant. Whatever pathway you choose.
Yeah, and ultimately in the long term, the savings will be huge.
Just out of a point of interest, how long is the lifetime of an electrolyser, Graham?
The full balance of plant has a similar lifetime to a conventional gas plant. Electrolysis stacks themselves more than 10 years. But what we do at ITM Power is we monitor all of our electrolysers in the field, and we do continuous maintenance and also recycling. So recycling and reuse is incredibly important. We're developing a circular economy for electrolysis, so that one of the things about PEM electrolysers is you can demount them. You can change out parts of the stack, or you can replace or reuse them. So I think very long is the answer.
Okay, and is that I think we've seen early on with other technologies, people had what turned out to be fairly conservative views of lifetime. When I think about solar PV or wind, I think especially with solar, we've seen performance and lifetimes better than originally expected. Yeah. Do you expect a similar thing with your electrolysers?
We're interested in the total cost of ownership. So what we're interested in doing is being able to reuse and recycle, but also increase longevity as well. And I think that's very, very important. We're also spending some time now looking at the amount of embedded carbon in producing the equipment. which I think has been a debate in the renewable energy industry. Of course, as the whole network decarbonises, then the power that you use to produce your product, the steel that's embedded in it, all of the materials that are embedded in it, the carbon footprint of those comes down. But I think two important principles, particularly for our own ESG credentials, are the amount of embedded carbon in the capital equipment that is used, and also the way that you apply a circular economy to that equipment.
One of the things we haven't touched on that I just wanted to get your view on, Graham, was the type of support that governments can give. And obviously we've seen, in a number of countries, promises being given for support for the capex for projects. In other countries, we've heard some discussions about carbon contracts for difference. And I just wonder whether you've got a view on what you think would be the most appropriate support mechanism to try and encourage the switch from, I guess, existing hydrogen production to green hydrogen production, or to encourage new uses, whether it's hydrogen being used for heat, hydrogen being used in steel, hydrogen being used in transport.
Yeah, a great question, John. So I would say, first of all, that for any use case, you have a business model. And to make electrolysis and green hydrogen investable, the business model needs to work. And that's a revenue model. So you put a capital asset on the ground, and it's then dependent on you having a positive revenue model. And if you look at green hydrogen, the business model is dominated by the cost of the renewable power, by the efficiency and performance of the electrolyser, and not the capex. So what you want is a CFD, not a capital grant. Now, there are circumstances, particularly smaller electrolysis that may be used for transport, where capital grants are very useful in the early days. But actually, you want a capital grant, but you want an RTFO, that's a renewable transport fuels obligation. Or in the case of grey hydrogen for industry, replacing it with green hydrogen, a CFD. And what that will do is drive volume, which will drive down prices. What you always want with an incentive scheme is one that brings in investment into the industry. And then you want one that drives the industry to volume and cost reduction to the point where there's no need for the subsidy anymore. So it's all about having a smart subsidy that drives the industry forwards, that can wither away within a decade. And that's what I've always said to the UK government. Make it smart, make it drive the industry forwards, increase scale, decrease costs, and then you only need it for a short period of time. And then market forces will take over.
Yeah. Do you think governments are moving quickly enough?
Some governments are. The UK government isn't. I think that, if you look at the amount of money that has been made available for green hydrogen in the UK, first of all, there's the Low Carbon Hydrogen Fund, which is 240 million. That is spread between blue hydrogen and green hydrogen. And there's a CFD which will be implemented in 2023, which is 100 million. We just raised 250 million on the London stock market, and we were 2.5 times oversubscribed.
Yeah.
I think that if you look at Germany, with 9 billion available for hydrogen projects over the next decade, and if you look at 150 billion across Europe, you can see that the UK government, first of all, doesn't have a significant enough vision for hydrogen or green hydrogen, and I think has not really understood the opportunity.
Yeah, and I think this week in the net zero strategy, there was, I think, 100 million to support 250 megawatt of electrolyser capacity by 2023. which, doesn't seem that ambitious.
No, I mean, we bid over the last 12 months, we've bid 1,011 megawatts of projects. We have a backlog of 310 megawatts of projects already. And across just 3 projects, we bid 560 megawatts of equipment. So some of our projects that we're bidding, so this is turnkey fixed price quotations against commercial tenders. Some of them are multi-hundred megawatt already. We are deploying electrolysers that are an order of magnitude larger every 2 years. This is logarithmic growth. 200 megawatts in 2023, we will have missed the boat.
So which countries are getting it right? You mentioned Germany. What about the Netherlands? Are they taking a good approach? Obviously, they've got the SD++ mechanism, which some say is good, some say isn't really working for electrolysis. Are there any other countries you think are really kind of leading the way?
Yeah, so if you look at national strategies and targets, there's about 150 gigawatts of national targets out there. That's electrolyser targets. It's all green hydrogen. The UK is the only place that is considering blue hydrogen. So if you look at those targets, then 6.5 gigawatts in France, 5 gigawatts in Germany, 5 gigawatts in Italy, 4 gigawatts in Spain, 2.5 gigawatts in Portugal. So Europe doing really well. Chile, 25 gigawatts to 2030. All of those targets, by the way, are 2030 targets, and they're all electrolyser targets. Chile, 25 gigawatts. Why is it so big in Chile? Well, actually, Chile has very high load factor, very low cost renewable power. It's a great place to make renewable ammonia and export it. If you look at the US just announced the Earthshot. So there are 5 projects in the US to propel the US to net zero. They've called them the Earthshots, and the first one announced was green hydrogen. Backed by the DOE and actually announced by John Kerry. Very significant emphasis on green hydrogen for the energy transition. Australia, moving incredibly quickly. You look at Japan and you look at Korea, developing end-use technology devices and industries with a strategy to import from all over the world. So it's an industry that is focused on green hydrogen, electrolyser targets, all of them are gigawatts in size. So, we have developed a 5 gigawatt strategy in the UK and 40 gigawatts of offshore wind. And if you look at Boris's 10-point plan, 5 of those 10 points have relevance to hydrogen. The offshore wind one, the 5 gigawatt target, sustainable marine and aviation fuel, low emission buses, and CCS. And my hope is that the market forces will show the UK government that green hydrogen and energy storage is the way of doing things rather than blue hydrogen.
Well, it's been a delight having you on, Graham, and hearing about all the developments on electrolysers, green hydrogen, and ITM Power. Thanks very much for joining us.
Thanks very much for having me. It's been a pleasure. And thank you to all your listeners for listening. And John, thank you very much for some great questions.
Yeah, thanks very much, John.
Thank you very much. A pleasure as always to talk with you, Graham.
Well, thank you very much for listening. I hope you enjoyed that podcast. Please subscribe to listen to more in our series Fueling the Energy Transition from AFRY Management Consulting. Thanks and goodbye.